Hello everyone. In this video, we're going to be going over a Markov chain example. So first of all, what exactly is a Markov chain? And a Markov chain, generally, it follows this formula here where we have this matrix vector product of a state vector or a probability vector here, and we'll call that sk plus 1. And this just basically just means that the state or the probability at the day or the iteration k plus 1, and this is equal to the matrix vector product of P, which is the stochastic or Markov matrix, times the previous iteration of our probability vector sk, or state vector. So it's just a matrix vector product, but we can do it for, it gives us the probability on the next day. So that is what a Markov chain is. Let's take a look at the actual example now. So we are given this big paragraph of a bunch of information, and it says adults aged 19 through 23 have been shown to be drinking either water, tequila, or nothing. So these are the only things that they can drink for the purposes of this example. So if an adult is drinking water, they have a probability of drinking nothing of 0.5 and a probability of drinking more water of 0.25 during the following hour. So breaking that down, that means that if they are currently drinking water, these are the probabilities that they will basically be going from drinking water to drinking water again the next hour, or drinking nothing the next hour. Okay? It also tells us if they're drinking tequila, then they have a probability of drinking tequila of 2/3 in the next hour. They also have a probability of drinking water of 1/6 in the next hour. And that's only if they are currently drinking tequila. So depending on what you're starting drinking as, either drinking water, drinking tequila, or if you're not drinking anything, this changes the probability of what you're going to drink next. Okay, so what we need to do to start off this question, let's start off to think, what exactly will our state vector or our probability vector look like? And the first question says to find the stochastic matrix P, but before we even start looking at that, let's make sure that we understand the question. Okay, so find the stochastic matrix P. Okay, let's take a look. Our steady state vector S, let's call it sk, or excuse me, not steady state vector, but just our state vector here, or our probability vector. It's going to take the form of let's call it tk, let's call it wk, and let's call it nothing, okay, so nk. So these values represent the entries of the vector. So let's let t sub k be the probability that you are drinking tequila on hour k. Okay, let tk be the probability you are drinking tequila at hour k. Similarly, wk would be the probability that you're drinking water at hour k. And you could imagine that nk would be the probability that you're drinking, or that you're not drinking anything on hour k. Okay? Great. Let wk, okay, and same thing, water, and let nk, that's the probability of drinking nothing. And all of these are for hour k. Okay, so you could imagine that if I said tk plus 1, Well, this would just be the probability that you are drinking tequila at hour k plus 1. So one iteration past k, which basically just means the next hour. And you can see that this is starting to look like we have some of this useful information in the question, because it is telling us some of the probabilities. You know, if you're drinking nothing, then it gives you the probability that you're drinking water the next hour or tequila the next hour, right? So we know that the next hour is signified by that k plus 1. So starting to connect the dots a little bit. Before we start getting into what exactly the setup of this question looks like, let's make sure that we understand the basics of probability, because this is quite important for this question. So when you have two events, and let's suppose that we had a hat, okay? And the hat has different objects in it, and depending on which object that I pull out of the hat, that will be a different probability. So let's say that in this box, okay, let's say that there's a red object, there's a green object, there's a blue object, and let's also have a yellow object right there, okay? And you can't see what's inside this box. So if I asked you, what's the probability that you pull out a red object? Well, this is pretty clear. It's 1 out of 4, right? Right? Okay. That might seem like common sense. But let's say that I said, okay, now what's the probability that I pull a red object or I pull a yellow object? And let's just, for the purposes of this example, you put the object back in the box after. So probability of red, well, we know that's 1/4, but the probability of pulling yellow, we know, okay, that's also 1/4 if we put the red object back. So if I wanted the probability that it's red or yellow, you would do 1/4 plus 1/4, okay? But let's do another example here, okay? What's the probability that I pull a red object and right after I pull a yellow object, okay? So this is different. The first example was, or the second example was, I pull a red object or I can pull a yellow object. This one is saying I need to pull a red object and then I also need to pull a yellow object. So out of the two picks, what's the probability that I will pull both a red and a yellow object? And in that case, since I need both of those things to happen, it's actually going to be 1/4 times 1/4 rather than 1/4 plus. So you can think of probability in like very fundamental examples. When you have the word or, that's basically telling you that you should add the probabilities. But if something and something else needs to happen, that means that you need to multiply the probabilities. Okay, so this is a basic example. Let's go back into our question now. Okay, so let's take a look at tk plus 1, and well, what are the different events, let's call them, that you could be drinking tequila the next hour? So I can think of one event. So event number 1. This could be you're drinking water at hour K, and then you start drinking tequila the next hour. Right? This is one event that could happen that would lead to me drinking tequila in the following hour. But this is only one event. Notice how that there's other ways that I could be drinking tequila at hour K plus 1. So, or, what about another event? How about what if I was drinking tequila and then I continue drinking tequila the next hour, right? So let's say, drinking tequila at hour K, and then tequila the next hour. Okay, and there's one more thing that you could think of. Try to think of that yourself for a second. So this last event, I could not be drinking anything during hour K, and then I just start drinking tequila, right? Drinking nothing at hour K. And then tequila next hour. So we wrote this out in terms of, words, but let's try to put this into some more mathematical terms. So tk plus 1. Okay. Well, first of all, event number 1, let's just look at event number 1. All right? Well, first, I need the probability that I'm drinking water at hour K. And we know that. We define that variable as W sub K. Okay. So W sub K. And then what's the probability? I need the probability that I am drinking tequila the next hour from drinking water. Right? Okay. Well, let's look at the question. Okay. If an adult is drinking water, they have a probability of drinking nothing of half, a probability of drinking more water of a quarter. So since the probabilities must add to 1, that means that the final probability of going from water to tequila needs to be a quarter as well. Okay? And since I need to be drinking water at hour K, and then this needs to also happen, that means I multiply the probabilities, right? So this is WK times 1/4. But this is only event number 1. Or event number 2 could happen. But remember, or, when we're talking about probability, means that I need to add this other event. I need to add this other probability. So let's do this, okay? Event number 2, I'm drinking tequila at hour K. Well, that we know was defined as T sub K. But now I need to know the probability that I'm drinking tequila, and then I'm also drinking tequila the next hour. And that I need to refer back to my question. So if they are drinking tequila, they have a probability of drinking more tequila of 2/3. So this TK needs to be multiplied by a probability of 2/3. All right, finally, event number 3. I'm drinking nothing at hour K. We know that that will be N sub K, as we defined. And then, so we multiply by the probability of drinking tequila the following hour of not drinking anything. So let's refer back to our question. If they're drinking nothing, they have a 3/4 probability of not drinking anything again, and an 1/8 probability of drinking water, which means that there must also be a 1/8 probability that they are drinking tequila. And that's because 3/4 plus 1/8 plus 1/8 needs to equal 1. So this will be NK times 1/8. Okay? And what was the point in all of this? Remember, this probability, the sum of those 3 terms, is equal to the probability that you are drinking tequila at hour K plus 1. So in other words, the probability that you're drinking tequila the following hour. It's the addition of all of these 3 separate probability events. Okay? So we also need to do this now for WK plus 1. We need to also do this for NK plus 1. Okay? And the whole goal of this is because this vector, TK plus 1, WK plus 1, NK plus 1, This is just our state vector or our probability vector for the Markov chain. Remember, back at the start of this question, we define, this is the Markov chain. We've got the following probability at iteration k plus 1 is equal to our stochastic matrix multiplied by the state vector s sub k. So I'm going to pause and try to come up with wk plus 1 and k plus 1 on your own, all right? And so pause the video right now, and I'm gonna fill out what these answers are. Just a sec. All right, so I've just filled out the other equations, okay? And now I've got my 3 different entries for that state vector sk plus 1, all right? So this is the equations that you should have gotten. And now what we're going to do, okay, well, we are going to put this into terms of a matrix vector product, all right? So this left-hand side, tk plus 1, wk plus 1, and nk plus 1. In terms of a matrix vector product, we can write the above system of equations as a stochastic matrix. Stochastic matrix just means that the columns of this matrix are probability vectors, aka they need to add to 1. So first column being all the tk's, we've got 2/3, 1/6, 1/6, right? This adds to 1. Okay, good. Wk, we've got 1/4, 1/4 and a half. And our last column, nk, is 1/8, 1/8, and 3/4. And this is our matrix, and it's being multiplied by this vector, and this is just tk, wk, and nk. So this matrix vector product is just describing the system of equations that we've written above. Notice that first column is like our tk column, our wk column, and our nk column, right? So you need to make sure that it's set up in this order. Perfect. So this is our Markov chain, right? This is our state vector sk plus 1. This is our stochastic matrix P, and it's being multiplied by the state vector sk, right? So the question asked us to find the stochastic matrix P. So the stochastic matrix P is just this matrix right here. So we've done what part A is asking us to do. Great. Part B says show that P is regular. So all that showing P is regular means is that we need to verify that the stochastic matrix has all non-zero and positive entries in each of the entries of the matrix. It's very clear without doing any sort of algebra that P is regular. We have all non-zero positive entries. So let's just write that out, okay? P is regular since all entries are positive, non-zero values. And that's all that you have to do for this question. So if you did have some zeros in this matrix, what you're gonna have to do is multiply the matrix P by itself. Find P squared. So this is just P times P. And you're gonna keep on doing this. So you might have to do P cubed. You're just gonna keep doing this until all of the entries are positive, non-zero values. And then once you've gotten there, you've shown that P is regular. So let's move on to the next question. What is the probability that an adult is drinking tequila 2 hours after drinking nothing? Okay, well, we've already described our Markov chain, right? Right here. This matrix vector product, okay? Let me copy and paste this. Okay. So tequila 2 hours after drinking nothing. Well, this just means k plus 1 is equal to 2, right? So I'm looking for S2, the state vector or the probability vector at hour 2, okay? But luckily, so to start off, we need to know what K0 is, or SK0, right? So for example, if this is state 1, when K is equal to 0, we have the probability matrix times S0. So this is our starting point, okay? We need to know the starting point. And we can find S0 from the question. It says the probability 2 hours after drinking nothing. It says after drinking nothing. This is telling us that the person is drinking nothing, 100%, all right? At K equals 0, we know that you are drinking nothing. This means that there's 0 probability you're drinking tequila, 0 probability you're drinking water, and 100% chance that you are not drinking anything at hour K equals 0. So all we need to do now is multiply this matrix vector product out. So this will give us T1, W1, N1. So we've got our matrix, 2/3, 1/6, 1/6, 1/4, 1/4, 1/2, 1/8, 1/8, 3/4. All of this times the vector 0, 0, 1. Perfect. So let's compute this multiplication. You should be able to figure out pretty quickly, since we've got 0 and 0 as the first couple entries, it's actually just going to be equal to an eighth, and 3/4. Okay, so this is state vector 1. Okay, so this is K equals 1, but the question is asking us what's the probability they're drinking tequila 2 hours after drinking nothing. Well, this is where the whole Markov chain comes in handy, right? Well, we're looking for this probability at K equals 2, right? And in order to compute this, it's probability matrix P times, and then it's 2 minus 1, right? So this is state vector 1. So we needed to start at 0, but we computed 1. And now we can use 1 in a new matrix vector product, okay? So now we're going to have to do this whole matrix again. 2/3, 1/6, 1/6, times 1/4, 1/4, 1/2, an eighth, 3/4. But now it's times S1, which is an eighth, and 3/4, okay? So computing this, let me start setting this up, okay? We know that S2, this will be 1/8 times the first column here, 1/6, 1/6, plus second entry of our vector, 1/8 times the second column of our matrix, 1/4, 1/2, and then the last entry, 3/4 times the last column of the matrix. Okay, so now this is just straight up algebra, okay, and the algebra should get you the values. Let me pull this up here. Should get you these values right here. 5/24, 7/48, 17/24. And I've written these out as decimals as well. So let's remember what this question is asking you. It's asking you what's the probability that they're drinking tequila 2 hours after drinking nothing. So this first entry is T2, right? So that represents the probability that someone is drinking tequila 2 hours from doing nothing because we started with S0 is 0, 0, 1. So this means that 5 over 24, or a roughly 20-ish percent, 21% probability that they're going to be drinking nothing 2 hours from doing nothing. Great. Okay. So question D. If one person is drinking water and 2 others are not drinking anything, what's the probability that all 3 people will be drinking tequila in the next 2 hours? Or, yes. Okay, so coming back to probability. The probability that all 3 people are drinking tequila in 2 hours from now let's clean this up a bit. This is going to be equal to the probability, and this P of is just a notation for the probability of this. Well, there's the probability that the one person who is drinking water, let's say, that they are drinking tequila 2 hours from then. And keyword here, remember, they are all drinking tequila. So it's not this person or that person. It's person 1 and person 2 and person 3. They're all drinking tequila. So we have to multiply all of these probabilities, okay? So then there's the probability that the one person drinking nothing is having tequila 2 hours later. Okay, so now we've got, this is the probability so far of the person drinking water and is drinking tequila 2 hours later, and the one other person is drinking tequila 2 hours later. But there's 3 people, right? And there's that one other person, so we need to multiply it by another probability here, and that's that same probability, right? That person who's drinking nothing is going to be drinking tequila, because we've got 2 people. Oops, how do I get rid of this? There you go. Right? Okay. And luckily, we've already solved for the second 2 terms right there, right? That is 5 over 24 because that person started drinking nothing. So this is 5 over 24 squared multiplied by this first term here, the probability that that one person drinking water is going to be drinking tequila 2 hours later. So this is T2 with S0 is equal to, they're drinking water, which means that T0 is 1, W0 is 1, or sorry, T0 is 0, W0 is 1, and N0 is 0, right? So you'd have to compute basically T2 again, but a different starting point. Instead of 0, 0, 1, it's going to be 0, 1, 0. And then we're going to do the same thing with our Markov chain. Find T2 in that case, because it will be a different probability. Multiplying all of those together, that will give you the probability that you're looking for this question. Finally, we've got find the steady state vector for this Markov chain. So what this is basically saying is, like, notice how every time there's a new iteration, it's changing our probabilities, right? So this is saying, is there ever a point where, you know, we keep iterating this Markov chain where you take the matrix vector product and the probability vector is just not going to change? So at this point, you could say that the probability vector or the state vector is going to reach a steady state where it doesn't matter once we do the matrix. We could keep doing the matrix vector product, but it's going to change such a little amount that it's considered at a steady state. So putting exactly what I just said into words, this is just like saying that SK is equal to the probability matrix or the stochastic matrix times the vector that we multiply it by. So if I take the matrix vector product of P and SK, it's just going to give me the same vector approximately. So that is what it's saying. So how do we solve for SK here? Okay. Well, solving for SK, we need to do a little bit of manipulating. If we move SK to the other side, so let's do SK minus itself, and we do SK minus SK on the other side. Well, take a vector and subtract the same vector. That will leave us with the 0 vector. And then we are left with PSK minus SK on the right-hand side. Or factoring out an SK, what we are left with is P minus the identity matrix times the state vector, SK. Okay? And the reason you can't just factor out an SK and do P minus 1 is because remember, P is a matrix, right? This is a matrix vector product equation, right? So it needs to maintain as a matrix vector product. We can't do P minus 1. That doesn't make any sense. That's not defined, right? But we know that P minus the identity matrix, if we were to multiply that matrix by a steady state, that is the equivalent statement. So it's a little bit different. You got to think about that before just factoring out blindly. Make sure that it makes sense in terms of matrix vector products. Okay, so how would you solve something like this? Well, you know that, okay, suppose that you had a matrix vector product, AX equals B. You know here that if you were to solve the matrix AB, simplify this, you know that the solutions to this matrix will give you the vector X. So looking at this, comparing this to the equation that we have, that means that if you solve the matrix P minus I is the left-hand side, and then that right-hand side is just the 0 vector. If you were to row reduce this, then the solutions would be the steady state vector. Right? So what we need to do is solve the homogeneous system of P minus the identity matrix. Okay? So let's get our vector or our matrix P here. Copy and paste this. So P minus I. So the identity matrix here is 1s across the diagonal and 0s in all other entries. This is going to be equal to 2/3 minus 1 is negative 1/3. 1/4 minus 1 is negative 3/4. 3/4 minus 1 is negative 1/4. All other entries will remain the same. Okay. So now we would row reduce this matrix because this is P minus I, right? We don't need to write out the column of zeros on the right-hand side. It's not going to change anything. But putting that matrix into reduced row echelon form, we are going to be left with this following matrix, okay? It's going to be 1, 0, negative 3/5, and then 3/10 here. 1, 0. negative 3/10. Let me double check this. Yes, great. Okay. So we're almost there. We're so close. So we know that reading the solutions off of this, okay, we can see that the rank is less than the number of columns of this matrix. 3 minus the rank, which is 2. That gives us one free variable or one parameter, and you can see that the column that has that free variable is that last column without the leading entry, right? So this is our n sub k column. So that means that n sub k will be our free variable, okay? Let's call this equal to t, which is, maybe t is not the best because we already used it. Let's call it lowercase r. So writing out the different solutions, we've got tk is equal to, this is going to be, well, it's tk, let me write it out very clearly. tk minus 3/5 r equals 0. We've got wk minus 3/10 r is equal to 0. And we've got, of course, nk is equal to r. So if tk is equal to 3/5 r, wk is equal to 3/10 r, and nk is equal to r, well, right now it's saying that we've got infinite solutions, which mathematically might be true for this matrix, but remember, this is a stochastic matrix, right? So, or at least in terms of the Markov chain, this needs to be a probability, this column needs to add to 1, right? So the probability of t, w, and n, they need to add to 1, which is telling us that 3/5 r plus 3/10 r plus r, right? All of the probabilities of drinking tequila, water, or nothing at the steady state, they still need to add to 1. So this is how we're going to solve for our parameter r. Okay? So this is going to be 6/10 r plus 3/10 r plus 10 over 10 r is equal to 1. This leaves us with 19 over 10 r is equal to 1, or r is equal to 10 over 19. So finally, tk is equal to 3/5 r, 3/5 r, which is 10/19. So this is going to reduce to something. wk, well, this is 3/10 r. R is 10 over 19. So this is more clearly 3 over 19. And nk is going to be equal to just r, which is 10 over 19. Okay. So what does this tk reduce to? This is going to reduce to 6 over 19. 6 over 19. Right, that totally makes sense. 10 divided by 5 is 2. 3 times 2 is 6. 6 over 19. So finally, we have found the steady state vector for this Markov chain. So once we reach a steady state, the probability that you're drinking tequila is 6/19. The probability you're drinking water is 3/19. And the probability that you are not drinking anything is 10/19. And this would be the final answer for the steady state of your Markov chain.